Now we will discuss vertical circular motion in case of a mass tied to a rod. Now to understand this mass tied to a rod in vertical circular motion, we need to discuss the difference between vertical circular motion with string and vertical circular motion with rod. The basic difference between the rod and the string in vertical circular motion is the string needs some tension at all the points in vertical circular motion. So the minimum speed at the highest position is root Rg, but in case of rod such condition is not required. Thus in case of rod at the highest position the speed can be 0. Here at highest position, even though the speed is 0, then also due to the property of inertia, this object will continue its vertical circular motion and will fall down and will perform the vertical circular motion. Whereas in case of string, if the speed of this object, if it is less than root Rg, then the string will become slack and the object will fall down and the vertical circular motion is not possible. In this diagram, we can see an object of mass m attached to a rod and performing vertical circular motion. At highest position, that is at point A, the weight of object, that is mg, is acting on the rod in downward direction. So the rod will exert the normal reaction N on this object in the upward direction. So the resultant of this is the centripetal force, which is essential for the circular motion. Therefore from this figure we can write mv square upon r plus n, that is normal reaction, is equal to mg. Here this v is the value of velocity at point A, so we can write va square. So this is mva square upon r plus n is equal to mg. This is the resultant force when the particle is present at point A. But for finding the minimum value, we can put this VA is equal to 0 at the top position, because as we have discussed, in case of a rod at highest position the velocity can be 0. So therefore we can write m, this VA is nothing but 0 square upon r plus n is equal to mg. Therefore we are going to get n is equal to mg. Now according to law of conservation of energy, we can write total energy at B, means at the lowest position, is equal to total energy at A, that is at the highest position. So we can write total energy at B is equal to total energy at A. This is nothing but kinetic energy at B plus potential energy at B is equal to kinetic energy at A plus potential energy at A. Therefore kinetic energy at B, we can write this nothing but half m VB square, where VB, it is the minimum speed at the lowest position, plus potential energy at B, that is mg, and h is going to be 0 because this point B is at the ground level, so this is 0, is equal to kinetic energy at A, that is half m VA square plus potential energy at A, that is nothing but mg, and this is total height from B to A, that is r plus r, that is nothing but 2r. Therefore we can write 1 upon 2 mvb square, this becomes 0, is equal to 1 upon 2 m, this VA. For finding the minimum velocity at the lowest position B, we are going to take VA, that is velocity at the highest position, at 0. So we are going to put this VO as 0. So plus this is 2 mgr. Therefore half mvb square is equal to, this becomes 0, is equal to 2 mgr. This m will get cancelled with this m, so we are going to get vb square is equal to 4gr. Therefore vb is equal to under root 4gr we can write this as 2 root gr. So this is the equation which gives us the minimum velocity of a particle which is attached to a rod at lowest position and performing vertical circular motion. Now we will discuss tension difference between lowest and highest position in vertical circular motion in case of a mass tied to a rod. In this case, as we had discussed earlier, at the topmost position, this object of mass m, its weight is going to be acting vertically downward, that is mg. So in order to balance this mg, there is a normal reaction by rod on this object which will be in the upward direction. Therefore, for this highest point, we can write tension at highest point is equal to mva square upon r minus mg. Here va is the speed of this object at the topmost position. And similarly, for this lowest position, we can write TB, that is tension at point B, is equal to mvb square upon r plus mg. Here Vb is the velocity of the particle at lowest position. Therefore, taking tension difference, that is TB, tension at point B, minus TA, that is tension at point A, we can write this as mvb square upon r plus mg and minus into bracket mva square upon r minus mg. Therefore, this TB minus TA, we are going to open this bracket, so we are going to get mvb square upon r plus mg minus mva square upon r minus it becomes plus mg. Therefore, TB minus TA, we are going to take m by r common from these two terms, so we can write m by r into bracket, this is Vb square minus Va square mg, we are going to get this is nothing but 2mg. But we know that at the lowest position the velocity of this object is, but we know that velocity at lowest position, it is nothing but root 4 rg, whereas at the highest position we have taken velocity at point A as 0. Now we are going to substitute these two values of Vb, that is velocity at lowest position, and Va, that is velocity at highest position in case of a mass attached to a rod in this above equation. Therefore, we are going to get this is Tb minus Ta is equal to this m by r into bracket Vb square, means we are going to get this is 4rg minus 0 plus 2mg. Therefore, this Tb minus Ta is equal to 4mgr upon r plus 2mg. This r will get cancelled with this r and we are going to get 4mg plus 2mg, we are going to get this is nothing but 6mg. So this is the tension difference between the lowest and highest position in vertical circular motion in case of a mass tied or attached to a rod.